We've spent the past couple of days studying properties of special quadrilaterals, and now we're going to look at how those properties can be used in proof. To prove that a quadrilateral is a rhombus, we can do any of the following. We can first of all use the definition and show that all of its sides are congruent, because we know that any quadrilateral where all the sides are congruent has to be a rhombus. We can show that our quadrilateral is first a parallelogram, and then second, it has perpendicular diagonals. And it's important to note that this says parallelogram with perpendicular diagonals, because the kite has perpendicular diagonals. And even though the kite has perpendicular diagonals, he's certainly not a rhombus. What makes him a rhombus is the fact that he's a parallelogram first. Likewise, a parallelogram with consecutive congruent sides also must be a rhombus. To show that a quadrilateral is a rectangle, you can use the definition and show that it has 4 right angles. You can say that he's a parallelogram first, and any parallelogram that has 1 right angle has to contain 4, because one of the properties of parallelograms is that its opposite angles are congruent. So if one of the angles is a right angle, his opposite angle is also going to be a right angle. And a second property of parallelograms is that consecutive angles are supplementary. So if one right angle or one angle is a right angle, the next consecutive angle in that quadrilateral also has to be a right angle. Or you can show that he's a parallelogram with congruent diagonals. Keep in mind that the isosceles trapezoid also has congruent diagonals. So you can't say a quadrilateral with congruent diagonals is a rectangle. It has to be a parallelogram first. And then the last one, to show that a quadrilateral is a square, again, you can use his definition and show that he has 4 congruent sides and 4 right angles. That's a lot of work. If you know one of the other 4 that's a shortcut, you're going to be doing or being a lot more efficient in your proof. You could show that he's a rectangle first, and if he's a rectangle, he automatically has 4 right angles. And then if you show that a pair of adjacent sides are congruent, that's also going to make him a rhombus, and anybody that's a rectangle and a rhombus has to be a square. You can show that he's a rectangle who has diagonals that are perpendicular, because again, that makes him a rectangle, and then the perpendicular diagonals makes him a rhombus, and being both makes him a square. You can show that he's a rhombus first, and a rhombus with a right angle is going to turn him into a rectangle, and somebody that's a rectangle and a rhombus has to be a square. Or you can show again that he's a rhombus first, but then show that he has congruent diagonals, and that will make him both a rhombus and a rectangle, forcing him to be a square. All right, so let's go ahead and take a look at the one proof that we're going to look at together. We've got this quadrilateral ABCD that's a parallelogram. Like always, anytime I'm given something that's a parallelogram, I'm going to use my highlighter to highlight him, and that'll be my indication in the drawing that he is indeed a parallelogram. We've got some perpendicular segments, and they've nicely marked those for us already in the diagram. And where we want to be at the end of the day by the time that we're done is we want to show that ECBF, so this guy here, is a rectangle. All right. Probably the best piece of advice I can give you with respect to any quadrilateral proof except the trapezoid, show that he's a parallelogram first. Parallelogram is always a good place to start. And in looking at that yellow parallelogram in the picture, I know that the top side and the bottom sides are parallel, because that's what a parallelogram is. He's a quadrilateral with both pairs of sides parallel. If I could get the left side and the right side of my pink quadrilateral to be parallel, then I would have a quadrilateral with both pairs of opposite sides parallel, forcing my pink quadrilateral to be a parallelogram. Well, if I look in the picture, I have a pair of congruent angles here and here. That's going to force these 2 lines, left side and right side, to have to be parallel. So that's the gist or the direction that I'm going to begin with this proof. I'm going to show that the top side is parallel to the bottom side, and I'm going to show that the left side is parallel to the right side. And for all you 2-column people out there, this proof is for you. I'm going to do a little statement and reason. So statement, reason, I'm going to go ahead and start out with the fact that ABCD is a parallelogram because that's how I knew that my top side was parallel to my bottom side. And then when I word this, I'm going to be a little sneaky, a little smart. I'm going to think about it as being a little smart. My top side is CB, but instead of saying CB is parallel to DA, I'm going to extend that bottom side to go from E to A. And the reason I'm extending that bottom side is so that it'll also include the pink quadrilateral that I'm trying to show as a rectangle. And that's because parallelogram has opposite sides that are parallel. And I'll cite statement 1 because statement 1 is where I had the parallelogram. All right, my next move is going to be to get the left side and the right side parallel to each other. So I knew these guys were parallel because of the perpendicular lines that were given to me. So segment CE is given to be perpendicular to segment EA. And in addition, segment BF is given to be perpendicular to segment EA. I'm also going to be a little smart about this. Notice that EA is perpendicular to both segment CE and segment BF. Because EA is perpendicular to both, it must mean that segment CE and BF are parallel to each other. Now, if you didn't see that relationship, you could use the right angles, which are congruent corresponding angles, to make those sides parallel. It would be just an extra step or two in your proof. So my reason for this, two lines perpendicular to the same line. And again, notice that in statement 3, both of those segments are perpendicular to segment EA, are going to be parallel to each other. And since it was statement 3 where I had those two segments or two lines that are perpendicular to the same line, I'll cite statement 3. And now in statement 2, I've got left side or top side parallel to bottom. In statement 4, I've got left side parallel to right side. So now I'm all set up very nicely to say that ECBF is a parallelogram. And that's because any quadrilateral with two pairs of parallel sides is, by definition, a parallelogram. I'm going to cite statements 2 and 4 because those were the statements in my proof where I talked about those two pairs of parallel sides. All right, at this point I've got a parallelogram, and if I sneak a peek up to the top to how to prove something's a rectangle, the second reason in that list says if I can show that just one angle is a right angle, that's going to turn my parallelogram into a rectangle. Well, I notice that this angle at E is a right angle because of the perpendicular lines. So that's going to be the direction that I'm going to go next in my proof. I'm going to talk about angle E being a right angle. And that's because perpendicular lines make right angles. And I'll cite statement 3 where I discuss the perpendicular lines. So now in statement 3, I've got my quadrilateral being a parallelogram. Sorry, in statement 5, I have my quadrilateral being a parallelogram. In statement 6, I have that parallelogram containing a right angle. Now I'm all set to go ahead and conclude that quadrilateral ECBF has to be a rectangle. And that's because any, and I'm going to be careful in my wording here, any parallelogram, note it says that it doesn't say any quadrilateral, any parallelogram with a right angle is a rectangle. I do want you to be careful when you write these proofs, because changing just one word in the reason, it takes a true statement to a false statement. This says any parallelogram with a right angle is a rectangle. If I had said any quadrilateral with a right angle is a rectangle, I would be mistaken. And that's because here's a beautiful example of a quadrilateral that contains a right angle, but he's definitely not a rectangle. So this must state any parallelogram with a right angle is a rectangle. All right, so like always, I'm going to have you go summarize the important ideas and key understandings that you need to recall from this video, and then see if you can apply your newfound knowledge to tackle that next proof on the next page.